Welcome to QOD video number 40. So we've made it up to 40. This is our last QOD for chapter 16, and it largely concerns itself with manipulation of tabulated data, specifically the type of various manipulations involving the Ka and Kb data that you can get out of Appendix D. So Appendix D is actually divided into three appendices. There's D1, which has Ka data. There's D2, which has Kb data. And then next chapter, we'll look at D3, which has what's called KSP data. We're not concerned with that right now. But what D1 does is it gives a bunch of Kas. But it's giving Kas for what we would call uncharged acids. That is, acids that are are neutral molecules in their protonated form. And so your book has an abbreviated table of data from from Appendix D1, and so you can see that for all these sort of common acids, chlorous acid, nitrous acid, hydrofluoric acid, hypochlorous acid, hydrocyanic, et cetera, all these sort of things that we would normally think of as weak acids, it gives Ka data. And the table itself in the back of the book actually looks like this. And so they're arranged in alphabetical order. And then it gives the name of the acid, the formula of the acid, and the Ka data. You'll also see sometimes what are called Ka2s and even Ka3s. And we'll talk about in just a little bit further on in this presentation what they mean. But what I kind of want you to focus on is the fact that all of these acids are uncharged in their protonated form. They're just neutral molecules. So that's a summary of Appendix D1 and the information it contains. Then there's Appendix D2, as I mentioned. This contains a bunch of tabulated Kb data for a lot of uncharged bases. And again, that is bases that are uncharged in their deprotonated form. And so there's also an abbreviated table of these in your chapter, and it looks like this. And what I mean by this is generally when we think of bases, we think of something with a negative charge like chloride or fluoride or acetate, things of that nature, bisulfate, phosphate, stuff like that. But there are some bases, as we've learned, where actually the base is a neutral molecule. And it's actually the conjugate acid that has a charge on it. It's got a positive charge. And so Appendix D2 itself looks like this. You've got a table D2. It lists by name about 10 of these nitrogen bases that are neutral in their basic form, and it gives their Kb values. So this leaves open a question, at least it leaves open a question for me because I've been doing this for a long time, which is, okay, Appendix D1 gives Ka data for uncharged acids like acetic acid or hydrofluoric acid, but it doesn't give any Ka data for positively charged acids. That is, these acids that are the conjugate acids of those nitrogen bases. Okay. On the other hand, Appendix D2, which gives a bunch of Kb data, gives data for uncharged bases like ammonia or aniline, but it doesn't give Kb data for any of the negatively charged bases that we normally think of, like acetate or fluoride or nitrite or cyanide or hypochlorite, things of that nature. So the question that this raises is, how do we find these data if we need them? If I need to know what the Kb of fluoride is, where is that information? It's not directly in Appendix D. If I need to know what the Ka of ammonium is, it's not directly given in Appendix D. Well, let me show you how we can figure this data out. Okay, and so consider this particular conjugate pair, hydrofluoric acid and its conjugate base, the fluoride ion. As I mentioned, the Ka of hydrofluoric acid is given in Appendix D, but the Kb of fluoride is not. Well, let's just briefly remind ourselves, for hydrofluoric acid, the ionization equilibrium would look like this. HF plus water gives hydronium plus fluoride. And the Ka expression would look like this. The products in the numerator, concentration of H3O times the concentration of fluoride over the concentration of HF. We leave water out. Okay. For fluoride, its ionization reaction with water looks like this. Fluoride plus water gives hydrofluoric acid plus hydroxide. And if we write the Kb expression for that, it's going to be products in the numerator, reactant in the denominator. Once again, we're leaving water out because it's the solvent. Okay. Well, what happens if we actually multiply these two things together? If I multiply Ka times Kb, that means I'm really multiplying these two expressions together, right? So if I multiply Ka times Kb, I am multiplying together their expressions. And if you look at these two expressions, you'll suddenly realize that I've got some things that appear in both the numerator and denominator when I multiply these things together. I've got fluoride in the numerator of the Ka expression, which is canceled out by fluoride in the denominator of the Kb expression. And I've got hydrofluoric acid in the numerator of the Kb expression, which is canceled out by hydrofluoric acid in the denominator of the Ka expression. And it turns out that when I multiply Ka times Kb, it all cancels out to just H3O plus times OH minus, which, as we learned earlier in this chapter, is called Kw, and it has a fixed value, which is 1 times 10 to the minus 14. And so it turns out that this is true for any conjugate acid-base pair. Ka and Kb for any conjugate acid-base pair are always related in this way, and that is that Ka times Kb is equal to Kw. And therefore, if you know one of them, you can calculate the other. And there's a table here that I just pulled this in. This comes from your textbook once again. And so this actually gives 3 of the 4 things that I had asked about earlier. Well, where's the data for this? Because your textbook gives the Ka for HF, the 6.8 times 10 to the minus 4th, you can calculate Kb for fluoride to be 1.5 times 10 to the minus 11th, because these two things multiply to give you 1 times 10 to the minus 14. Similarly, Appendix D1 gives you the Ka value of acetic acid as 1.8 times 10 to the minus 5. Therefore, you can calculate the Kb of acetate as being 5.6 times 10 to the minus 10, because these two numbers, when multiplied together, give you 1 times 10 to the minus 14. Appendix D2 gives you the Kb value of ammonia as being 1.8 times 10 to the minus 5. Therefore, you can calculate the Ka value for ammonium is 5.6 times 10 to the minus 10th. These two numbers multiplied together give you 10 to the minus 14. So what would a problem look like in which you were given some data and asked to do a calculation? Okay, so here's what I'm asking you to do. Determine the following K value. The Kb of cyanide, the Kb of nitrite, and the Ka of what's called anilinium, which is the conjugate acid of a nitrogen base called aniline. So you can, if you want to try these, you can pause the video right now and look for these data in Appendix D, and then calculate the answers. Well, let's take the first one, the Kb of cyanide. Appendix D1 tells you that the Ka of hydrocyanic acid is 4.9 times 10 to the minus 10th. Therefore, when I divide Kw by 4.9 times 10 to the minus 10th, I get the Kb of cyanide, which is 2 times 10 to the minus 5th. What about the Kb of nitrite? Well, Appendix D1 tells you that the Ka of nitrous acid is 4.5 times 10 to the minus 4th. So to get the Kb of nitrite, I divide Kw by Ka, and that gives me the Kb of nitrite as being 2.2 times 10 to the minus 11. What about the Ka of anilinium? Well, now Appendix D2 tells me that the Kb of aniline is 4.3 times 10 to the minus 10th. 10 to the minus 14th divided by the Kb of aniline gives me the Ka of anilinium, which is 2.3 times 10 to the minus 5th. So you can use the tabulated data to either obtain, you can use the tabulated data to obtain the Kas of the listed acids and the Kbs of the listed bases. And then you can use this Ka times Kb equals Kw relationship to determine the Kbs of all the acids that are listed in Appendix D1 and determine the Kbs of the conjugate bases of all the acids that are listed in Appendix D1. And you can also use the same formula to calculate the Kas of the conjugate acids of all of the bases that are listed in Appendix D2. Let's move on. Oh, and so here's what this allows us to do. It allows us to go back and take a look at this, this diagram we had of acids ranked by strength, in which we've got them binned into strong, weak, and negligible on both sides. We can actually assign quantitative values to these now and say that weak acids are acids whose K values are less than 1 and greater than 10 to the minus 14th. Which is another way of saying that they are weaker acids than hydronium, but they're stronger acids than water. Well, based on that Ka times Kb equals Kw, what we can figure out from that is, since all weak acids have Kas between 1 and 10 to the minus 14th, it turns out that their conjugate bases all have Kbs between 1 and 10 to the minus 14th, which makes them all weak bases. Now we have defined strong acids as having K values greater than 1. Using the Ka times Kb equals Kw, what that means practically is that if things that are negligible bases are negligible bases because their Kbs are less than 10 to the minus 14th. In other words, they are worse at deprotonating water than water itself is, and so they won't have any effect. We can define strong bases as bases whose Kbs are greater than 1, and therefore their conjugate acids are going to be negligible because they're going to have Kas that are less than 10 to the minus 14. In other words, they are worse at protonating water than water itself is, and so they're essentially not going to have any effect on pH. Now let's move on and talk about polyprotic acids. And I've shown this picture here again of Appendix D1 because I mentioned when we were talking about it earlier that in addition to all these K values, you'll occasionally also see a Ka2 and a Ka3. And that's because anytime you see that appearing, it's because it's a polyprotic acid. So arsenic acid has three ionizable hydrogens. Therefore, it's going to have 3 different Kas. Ascorbic acid has 2 ionizable hydrogens. Therefore, it's going to have 2 different Kas, etc. There is, once again in your book, an abbreviated version of this, table 16.3. And this is just sort of highlights, but ascorbic acid has 2 ionizable hydrogens. Therefore, it's got 2 different Ka values. Carbonic acid, 2 ionizable hydrogens, 2 different Ka values. Citric acid and phosphoric acid, you'll notice each has 3 ionizable hydrogens. Therefore, it has a K1, a K2, and a K3 for citric acid, and similarly for phosphoric acid. What you'll notice about these is that they are different from each other. No 2 Ks for the same polyprotic acid are the same. They keep getting smaller. So each acidic hydrogen atom of a polyprotic acid has its own Ka value. And what you will notice is they keep getting smaller, which means that those hydrogens become more and more successively difficult to remove. It is the second ionization is a weaker equilibrium than the first, and the third ionization is a smaller equilibrium than the second. Okay. So let's just take an example, sulfurous acid. Sulfurous acid is right here. When you put sulfurous acid into water, there are actually two ionizations that occur. The first one is in which sulfurous acid ionizes into H plus and bisulfite. The second one is in which bisulfite further ionizes into H plus and sulfite. And they're governed by two different equilibrium constants. This one, Ka1, is 1.7 times 10 to the minus 2. Ka2 is 6.4 times 10 to the minus 8. So while in both of these forms, both of those deprotonations represent a weak acid, this one is much easier to do than this second one. And because of that, because the successive Ka values are usually much smaller than Ka1, we can generally ignore them when we're calculating the pH of a polyprotic acid. In other words, if I gave you a problem in which I asked you to calculate the pH of a 0.1 molar solution of sulfurous acid, you would really only have to consider the first ionization, because the second ionization is so much, this is already a small number, and this one is much, much, much smaller. So compared to the first ionization, the second ionization is just sort of insignificant, and the third ionization, in addition, would be insignificant compared to the second one. Well, that's as far in this video as you need to watch. But I'm going to go on and talk about just a few more things of interest to me, and also questions that have come up over the course of the chapter in the discussions in class. But these will not be on the QOD. If you go back to the calculations we were doing when it came to calculating, if you know initial concentrations and you know the value of Ka, that you could calculate the final concentrations and therefore the pH. And you'll remember we got to this point where we decided that 0.3 minus x was essentially equal to 0.3, and that we were going to avoid a quadratic equation by simply ignoring this minus x and assuming that because this is fairly close to 0.3, we can just pretend that it is 0.3. And that's very convenient because it allows us to avoid a quadratic equation. The question that has come up from more than one quarter about this is, when are we able to make this assumption? Can we always make this assumption when we're doing a problem like this? Or can we only do it sometimes? Well, it turns out that the answer to that is that if x winds up being less than or equal to 5% of this original concentration of the weak acid, then we can ignore x. And if you do this calculation, you'll find actually in this case that that x is much less than 5% of 0.3. And so we wound up being justified in making that assumption. But of course, that means that you have to actually do the calculation, make the assumption, and then do the calculation to figure out whether the assumption was justified. Except that you actually don't, because there's a simple little workaround for this. And that is, if you take that initial concentration and divide it by the value of Ka for the given weak acid, and if you find that that number, dividing this number by Ka, gives you a number that is greater than or equal to 400, then that means that the value of x is going to be less than or equal to 5% of HA, and therefore your assumption is going to be justified. And so let's look at a couple of examples of this. We'll look at acetic acid and we'll look at hydrofluoric acid. So suppose you get a question that says, calculate the pH of a 0.1 molar solution of acetic acid, and the Ka of acetic acid is equal to 1.8 times 10 to the minus 5. I want to know whether or not I can make that assumption that x is so much less than 0.1 that I could ignore it. And so I take that initial HA concentration, 0.1, I divide it by the Ka of acetic acid, 1.8 times 10 to the minus fifth, and I get 5,556, which is greater than 400. So it is okay for me to make that assumption that X is negligible, and I can simply take it out of the equilibrium constant expression and therefore avoid a quadratic equation. What about HF? Same concentration. Calculate the pH of a 0.1 molar solution of HF. The Ka of HF is 6.8 times 10 to the minus 4. Well, if I take that 1.1, that initial concentration, and divide it by K, I wind up getting 147. That is less than 400. Therefore, it's not okay for me to make the assumption that X is negligible compared to 0.1. And I'm going to have to go through a quadratic equation. And so without drawing this out into excruciating detail, let me just prove to you that why this works or doesn't work, as the case may be. If I take the acetic acid example and simply assume that the X is negligible, and therefore 0.1 minus X just becomes 0.1, I solve that and I get a value for X of 1.3 times 10 to the minus 3. If I leave that X in, that actually forces me to go through a quadratic equation. When I do that, and when I use the quadratic formula to solve that quadratic equation, I get X equals 1.3 times 10 to the minus 3. And so it didn't matter that I went through the quadratic equation. The answer wound up being the same in both cases. If I look at the hydrofluoric acid example, and remember I said in this case I'm not justified in removing the X from the 0.1 minus X. If I do it anyway and do the calculation, I get X being equal to 8.3 times 10 to the minus 3. But if I leave it in and solve it as a quadratic equation, I wind up X being 7.9 times 10 to the minus 3. So you can see that if that number is less than 400, if dividing the initial concentration by the Ka gives you a number that's less than 400, then there is a significant difference between the values of X that I get from taking the X out and leaving it in. Okay, finally, a challenge question for you. Bicarbonate is amphoteric. That is, it is both an acid as a base and a base. It could donate an H plus to be an acid, or it could accept an H plus and act as a base. So that raises the question, if I make an aqueous solution of bicarbonate, is that going to be acidic, or is it going to be basic, or is it going to be neutral? And so I'm leaving you as a challenge to see if you can use the data in Appendix D1 and what we've learned in this chapter, in this video, about the relationship between Ka and Kb, and figure out whether bicarbonate, a solution of bicarbonate, will be acidic or whether it will be basic. Okay, thanks for watching. There will be practice problems suggested, and we will look forward to seeing you in class. Bye-bye.